Hello, everybody. Thank you for joining our young seminar series. And we are always happy to see so many participants. So today it's actually the last young seminar series in this year. So small celebration. And unfortunately, we have to have 3 speakers, but one of our speakers couldn't make it today. So Roy Naveiro cannot join us today, but we hope that probably next upcoming seminars he can make it. And so we have today 2 great speakers, and we are very looking forward to see their research. So just small remind, as usual, we postpone all questions to the end of the all talks, but if you have some urgent problems or questions, you can type it in the chat or raise a hand. We can unmute you and give you a permission to ask an urgent question. So our first speaker, Antonio Sudoso, he's from University of Rome or Vergata from Italy, and he will be presenting today to us his great research. So we are looking forward to listen it. Floor is yours, Antonio.
Okay, first of all, I would like to thank all the organizers for the invitation, and I'm going to show you part of my PhD thesis that is SOS-SDP, a global optimization solver for the minimum sum of square clustering problem. And this is a joint work with my supervisor Veronica Piccialli and Angelica Wigele. So let's start from the problem definition. Given n data points in RD, the objective of the minimum sum of square clustering, or in short MSSC, is to partition them in k-clusters such that the sum of square the differences between each point and the cluster center is minimized. So from the optimization point of view, it can be formulated as the following mixed integer nonlinear programming problem. Where here we have delta ij representing the assignment variables, that is delta ij is equal to 1 if the data point I is assigned to the cluster j and 0 otherwise, and then mj are the cluster centers. So this is a simple model, but it shows some difficulties from the mathematical optimization perspective, since it is an NP-hard problem. It's known to be NP-hard from the theoretical point of view. So here we can see that the objective function is highly nonlinear, and we have binary and continuous variables. So let's start from the reformulation of the mixed integer nonlinear problem for the clustering. And back in 2007, Peng and Wei reformulated the MSSC as a nonlinear semi-definite programming problem, which here we minimize a linear function subject to some constraints. So the row sum is equal to 1, the trace of k is equal, the trace of z is equal to k. Z is element-wise non-negative, is symmetric, and z square is equal to z. So here, WP is the data matrix, which can be obtained by stacking the data points I and xi, and then W is the linear kernel, which is the matrix containing the inner products of the data points. So here they simply moved the nonlinearity from the objective function to the constraints. And in fact, here we have a very difficult constraint that is z square equal to z. In fact, from the last constraints and z being symmetric, we can see that the eigenvalues of z are only 0 and 1. So this is a very difficult constraint to handle. So these two problems are equivalent. And here, now let's see the structure of any feasible Z for the Peng-Wei reformulation of the MSSC. We can see that Z is a block diagonal matrix with a very nice structure. fact, if the data points I and J are in the same cluster, let's say the cluster C, then the row I and the row J of Z are equal, and the non-zero entries of these rows are equal to 1 over the cardinality of cluster C. Otherwise, if data points I and J are not in the same cluster, then simply Zij is equal to 0. So as an example, here we consider a small example consisting of 6 points in 3 clusters. Here we have on the left x1 in the first cluster, x2 and x3 in the second cluster, x4, 5, and 6 in the third cluster, and on the right we can see the block diagonal structure of a feasible clustering matrix Z. Okay, so here the objective of this talk is SOS-SDP, which is a global optimization solver consisting of a branch and bound algorithm for solving the MSSC. And I'm going to show you the ingredients used in our algorithm. First, we start from doubly non-negative relaxation for computing good quality lower bound. Then we introduce a cut-in plane procedure for strengthening the lower bound. Then we exploit the structure of the clustering problem by means of a tailored branching strategy. Then we have a primary heuristic, which is based on the classic K-means algorithm. And K-means algorithm is a local optimization procedure, so it is known to be sensible to the choice of the initial cluster centers. So here we propose a semi-definite programming-based initialization to seed the primary heuristics. So let's start from the SDP relaxation. The Penguin formulation can be rewritten as an equivalent SDP with an additional rank constraint. Here we simply replace Z equal to Z transpose and Z square equal to Z by these two constraints. The rank of Z is equal to K and Z is positive semi-definite. So here, by simply dropping the non-convex rank constraint, we end up with the semi-definite relaxation, which is actually a doubly non-negative relaxation, since the optimization variable Z is constrained of being at the intersection of the positive semi-definite cone here on the right and the non-negative ortant, because Z is element-wise non-negative. So now let's see the classes of inequalities we use in order to strengthen the bound. Here we consider 3 classes of inequalities. Let's start from the pair inequalities. In any feasible clustering, we have Zij is less or equal to Zii. Then the triangle inequalities, the idea behind these inequalities is that if the data points I and J are in the same cluster and I and H are in the same cluster, then J and H must be in the same cluster. And this relation can be expressed by the following linear constraints. Then we have the clique inequalities. Here the idea is that for any subset Q of cardinality K plus 1, where K is the number of clusters, then at least 2 points must be in the same cluster. So here we have the following linear constraints. So as for the branching decision, we produce a binary enumeration tree, in the sense that here we have a cannot link node. We say that if the points I and J are in different clusters, then they cannot link. And then in this case, we simply add the constraint Zij is equal to 0 to the SDP relaxation. And then if the data points I and J are in the same cluster, then we are in a must link node, I and J must link. And then we simply add the constraint that the row I and the row J of Z are equal. So here you can see the structure of the cannot link subproblem on the left and the must link subproblem on the right. Okay, as for the branching pair, we know that in a matrix Z that is a feasible clustering, for each pair I and J, either Zi is equal to 0 or Z rho I is equal to Z rho J. So here we use a simple branching strategy which reflects the way we partition the problem, and here this is our choice to select the points, data points to branch on. So here we can observe that the mass link subproblem can be reduced to a problem of size n-1, in the sense that we can we can select data points involved in mass link constraints, and we can merge them into a single data point. In fact, here we can reduce the size of the WP, the matrix WP consisting of the data points, by substituting rho I by data points pi and pi j, and we can omit the rho j. As an example, here we consider a series of branching decisions, and then we introduce a transformation matrix that keeps into account the data points that have been merged so far during our branch and bound search. And this transformation matrix applied to our optimization variable allows us to reduce the size of the problem from n to n-L, where L is the number of mass link constraints. In particular, here we can see that the problem on the left and the problem on the right are equivalent. The problem on the left is the general problem, the general subproblem encountered in the branch and bound whenever we had mass link constraints, and the problem on the right is the equivalent problem. The difference with respect to the problem on the left is that the problem on the right is still a W non-negative relaxation, but it is a semi-definite programming instance over a lower dimensional positive semi-definite cone, which is more efficient to solve. In fact, the size of the problem on the left is n, where n is the number of data points, and the problem on the right has size n-L. So as for the upper bound procedure, we simply exploit one of the most popular machine learning algorithms, that is the K-means. K-means is a local optimization procedure that consisting of two steps. In the first step, we perform the optimal assignment of the data points to the cluster given the cluster centers, in the sense that for each data point, we assign each of them to the closest cluster center. And then in the second step, we perform an optimal choice of the centers given the current, given the cluster. That is, we simply compute the centroids of the data points for each, the mean of the data points assigned to each cluster. And we use them as new centers. So these two steps are repeated until the solution does not change. And of course, the drawback is that K-means is efficient, but is a local optimization procedure, and it relies on the choice of the initial cluster centers. So in order to solve this problem here, we propose also we use also a constrained version of the K-means algorithm that can handle pairwise constraints, namely mass link and cannot link constraints. So our constrained version of K-means is inspired by a very famous paper about constrained clustering proposed by Wagstaff in 2001. That is a straightforward extension of the classical K-means algorithm. In fact, for each data point, we assign each of them to the closest cluster center, such that no pairwise constraints are violated, and then, like K-means, we simply update the cluster centers by taking the mean of the data points assigned to each cluster. And these two steps are repeated until convergence. So here we can see that the quality of the upper bound in our branch and bound algorithm depends on the quality of the heuristic, the quality of k-means. So here we use a semi-definite programming based initialization. So given a feasible z for the Penguin reformulation, that is a rank k matrix, so the original problem, if we post-multiply the clustering matrix Z by WP, which is the matrix containing the data points, we end up with a matrix M that contains exactly k repeated rows, and each of them represents the center of a cluster. So the intuition is that if the SDP relaxation is close or being tight, then the rows of M are close to the optimal cluster center. So, for example, if we solve the semi-definite programming relaxation and we end up with the clustering matrix Z that is having a rank K, then we simply say that the semi-definite programming relaxation is tight, and we need to extract the optimal cluster centers by using this procedure. But if the relaxation is, in practice, the relaxation is far from being tight. So we need a sort of rounding procedure. So here, the idea is to extract the near optimal cluster centers by looking at the solution of the SDP. So here we follow the steps. First, we solve the SDP relaxation at each node, and we obtain a minimizer Z hat. Then we find the best rank K approximation of Z in terms of the Frobenius norm, and this task can be achieved by computing the eigenvalue decomposition, the truncated eigenvalue decomposition, and taking the K largest eigenvalue. Then we simply compute our proxy for the centroids, the matrix M. Then we cluster the rows of M by using unconstrained k-means, and we use, in order to extract the initial cluster centers, and we use them to initialize the constrained version of k-means for the upper bound computation. So we did several experiments in order to show the effectiveness of the proposed initialization procedure, and we obtained better results than multi-start with k-means or more sophisticated initialization techniques such as k-means plus. So here I want to give you some implementation details. Our global optimization solver is implemented in C++, and we use SDP null plus in order to deal with the doubly non-negative relaxation, which is implemented in MATLAB. So SDP null plus is basically a large-scale solver for SDPs, and it uses a first-order method to deal with the SDP. And we solve each of them to medium precision that is 10 to the minus 5 in terms of the KKT residual. And of course, we also implement a procedure in order to obtain a safe bound from the solution of this TP relaxation, which in principle can be obtained by solving SDPs to higher precision, which is out of reach when using, for example, first-order methods. So this is the machine we used for the experiments. And of course, we provided a multi-thread implementation. So whenever we create a must-link and cannot-link subproblem, we submit them to a pool of threads, and each of them is run in parallel with the other threads of the pool. So let's see now the state of the art. Global optimization algorithm for MSSC are not very common to be encountered in the literature. Mostly because of the computational complexity of the optimization model. However, here we have some algorithm. Let's start from the column generation algorithm proposed back in 1999, but it can solve instances up to a few hundreds of data points. Then we have a repetitive branch and bound by Brusco proposed in 2006 that can solve larger instances, but also performs poorly when for poorly separated clusters instances. And also, to the best of our knowledge, the previous state of the art was the column generation algorithm proposed in 2012, and it is the first large-scale solver for the MSSC, but it can solve instances up to 1,000 data points, but only in the plane, or when the ratio between n and k is small. So. So these are the characteristics of the 34 data sets we used for our experiment. We managed to solve all of them. We started from the smallest one, which is consisting of 75 data points in the plane, and then we managed to solve also very large scale instances such as the last one here, consisting of more than 4,000 data points. And also here we can see that the number of features are not relevant in our algorithm, since we managed to solve instances with a huge number of features. For example, here we have more than 20,000 features. So here, as a summary, we solve for the first time large-scale instances with a huge number of features for different values of k. Here we, in order to choose the suitable number of cluster k, we use the cluster validity indices. For example, the elbow method or the silhouette method. And then, of course, the bounding procedure and the cutting plane algorithm is fundamental for deriving very good lower bounds. And in fact, we can see that the number of nodes is very low. But the single node can be expensive, since we need to solve more than one XDP in a cutting plane fashion. And on 44% of the instances, we certify the global optimality for a clustering that k-means cannot find at the root node. So this is the code. So if you want to give a look at the code, the source code, and the instances, you can reach this website. And that's all. Thanks for the attention.
Thank you very much for your nice presentation, Antonio. I don't know if Veronica Pisiali wanted to add something. She raised her hand. If not, well, we can go to our second speaker. I recall you that we will place the questions till the end. So our next speaker is Giorgio Grani. He's a research scientist at SINTEF Digital from Norway, and today he's talking about job shop and train dispatching via deep reinforcement learning. The floor is yours, Giorgio.
Okay. I don't see the screen right now.
Wait. Sorry.
Okay. So good evening, everybody. I'm Giorgio Grani, and I'll present today a couple of works that we have done at SINTEF in collaboration with Sapienza, University of Rome, and Optrail, which is a company that does optimization for railways. So let's start. Now we'll talk a little bit about reinforcement learning. It will be mostly applied stuff. So why not talk about reinforcement learning a little bit at first? So what reinforcement learning is, it's the third paradigm of machine learning alongside with supervised and unsupervised learning. And basically you have an agent and an environment that interact with each other. The agent basically see a codification of the environment called the state as of t, and does an action a of t. Then the environment sees this action and perceives a modification and communicates this modification to the agent with the next state, the st plus 1. And additionally, there is a reward rt plus 1, which is kind of a benchmark used by the agent to optimize his objective. Oh, sorry. Okay. So some notation here, pretty simple. So states are called with S, actions with A, and rewards with R. What the same can be said for the sets. So capital S is the set of all possible states, capital A is the set of all possible actions, and R is the function associating states and actions to rewards. This is a function because the problems that we are going to see are thought to be deterministic for the single instance that we are going to solve. Another important name that we are going to use is the policy, which is basically a probability function saying the probability of choosing a certain action A. Sorry, try to use this. Yes. Okay. So a certain action A after we observe a state as of t. And this group of functions, this function will define our strategy, so our decisions through the process. The objective, as I said before, is to maximize the expected cumulated reward from the start t equal to 1 to the end capital T when we follow a certain policy. So it's the expected when we are under pi. A couple of good of important functions that we are going to use in the algorithm that are presented below are the state value function, which is the expected cumulated reward when we see a certain state. So if we are in the state S of k, then that's basically the best the mean that we are going to get following our strategy pi. Whether the advantage function is can be seen as a differential between the reward we observed as state k, the expectation that we have from the state k plus 1, minus the expectation we have for starting from sk. So basically the difference. Okay, we will use some type of algorithms that are called actor-critic methods, and to understand actor-critic methods, it's maybe easier to see just the gradient here, which is the gradient of the cumulated reward that can be approximated in this way, where we have a part which is driven by the policy and another part which is driven by the advantage function. So in actor-critic, there are these two players, one approximating the policy and the other one approximating the advantage function. So if we go to the picture, which is slightly different from the picture I showed you in the first slide, the main difference is that here, instead of having a big agent, we split the agent into two, the actor and the critic, and the reward and the state affect each other in a structured way. Okay, so deep breath, and now let's go to the first problem, which is the train dispatching problem. So this is a joint work with Valeria Gasucci from University of Rome and Optrail, and Leonardo Lamorgese from Optrail. What is the train dispatching problem? So this is the Norwegian rail system, and as you may see, there is a hub in Oslo, and all the lines are more or less connected to that hub, and they can be also pretty long. The major thing is that on a normal situation, a normal day, you want your train to be on time, right? So to respect the schedule, but this doesn't happen in general because there could be a lot of disruption. And with a structure right there, this disruption may propagate delay through the whole network. So a delay starts at the top, like in Trondheim, then it can go down to Bergen just because it went through Oslo. And of course, maybe in Norway there is not that big traffic as you may see in other places, but there is something called a lot of snow. So this is quite beautiful, but most of the problems that are involved with the railway system are actually due to bad weather conditions. So it could be floodings, it could be ice, or it could be snow in general, snowstorms, or also wind on the coast, of course. So the train dispatching problem is to finding a rerouting and a rescheduling solution, taking into account the whole railway and traffic information, minimizing a suitable cost function. This could be the total delay or the average delay of the system. There are two problems here. First, of course, spoiler alert, the problem is NPR. That's, yes, we know that. And the second thing is actually we need to find a suitable solution in few seconds because we need to send our solution to the actual dispatchers, which are the one with the physical responsibility for the choices. So every time we got a solution, it has to be sent up. Let's say 30 seconds per solution. So we need something which is fast. So we thought about, of course, reinforcement learning. Now I will show you something about the railway representation. Now we can cast the train dispatching problem into the reinforcement learning framework. Yes. Okay, so of course here I'm a little bit simplifying because these are real world problems. So there are a lot of business constraints and technical and physical constraints. But just for us, just to understand a little bit where we are now, we may say that in a network there are stations and tracks, of course, and between station and tracks, each component on the railway can be seen as a resource, can be called resource, and there are a lot of different resources. So, for instance, there are stopping points or platforms, if you want, where you can board or alight passengers and goods. Crossovers where they're needed to change the order of the train for strategical stops. Then there are switches and signals and for each train we have a direction, a priority, and a length, and it's actually the length the one affecting the most the complexity of the problem, because trains can occupy more than a resource at the time, especially if they're very long. Okay, infeasibility in these problems arise when there is a deadlock. So a deadlock is basically a situation when two or more trains cannot move anymore in the network. So the network is stuck and there is a major disruption. And on theoretical, so from the model point of view, a deadlock implies an infinite amount of delay. So of course this doesn't appear in reality, but what may happen in reality is something like that, where of course there will be no infinite delay likely, but of course some hours of delay to get out of this weird situation. The decisions that we can make at each time are three types. So the first one is stopping the train. The second is going to the best resource, and the third is going to a reachable resource. What is a reachable resource? It's basically a suboptimal one, which is a little worse than going to the best, but better than just a quit and wait, accumulating delay. The reward is computed after a full solution is computed, so after a rollout, and it's basically the difference between the actual and the free running time. And when we have a deadlock, we assume a penalty value. For this problem, we chose to use the advantage actor critic. The advantage actor critic was first proposed in 2016. And the structure is basically articulated in two levels. The first one is the lower level, where there are workers, and each worker does a complete rollout. So doing a complete rollout, it accumulates the information for the gradients for the policy and the value function for that particular rollout, and then the coordinator takes everything together and updates the global function to be used for the next step. Does it mean it's in mathematical formulas that basically, these are the worker gradients, one for the policy and the other for the value function, and then when we need to update policy and value function, we do a gradient ascent or descent step, taking the average of those gradients. Of course, the railway has a graph structure, so we decided to use a graph neural networks to as the brain for both the actor and the critic. And just to be short, a graph neural network, it's a neural network that takes as input a graph, and this graph has for each node, for instance, a vector. It could have a vector of features, and now we will call we will also consider the neighborhood of each node. Why we are considering the neighborhood of each node? Because then for each node we are doing some graph convolutions, which means that we are including some basic operations per node. So the first one is where we do a mean over the features in the neighborhood. The second one is it's a simple ReLU, where we take our node and the value computed in the first operations, and then we do a second round of ReLU with using the embeddings of the first round. And of course, this type of operations can be done several times inside a graph convolutional neural network, and in our case, we did it 3 times. So at the output of the network, so at the end, there is a function, and this function is a function of the embeddings, and of course, the dimensionality of the output depends on what we need to do. For instance, in the actor, the dimensionality is in the dimension of the decision space, whether for the critic it's just a scalar because it has to approximate the valid function. Then we see how it goes. Let's see. So I'll be short. So then we chose to use this 2 tracks network with 131 resources, 40 single track, 14 multiple, and 63 stopping points. So this is driven by US class 1 real world network, and where of course we had some instances and some other we have simulated out of it, but the structure, the physical structure is the same. And yeah, the length of the train can vary from 4,000 feet to 12,000. We have 5 levels of priority, sorry, and we trained on 100 instances for 10,000 episodes. And I will show you some comparison with actually ourselves from 2020 and Kadilkar from 2018, which was kind of the previous work in this kind of settings. So it's all about learning here. We are still working on comparing ourselves with exact methods. Since we're both in SINTEF and in Optrail, we work with exact methods also. So, but we are still far to show the results on that kind of approaches. So I'll show you just on the learning side of the manner. But the important thing is that we test out on 2 tasks. The first one with 500 instances drawn about the same distribution as the training set, but unseen instances. Whether the second considers a higher number of trains and longer trains. So it's kind of considered a little bit of generalization of distances of the training set. And what we experience is that basically the GNN approach outperformed the others in terms of delay in both cases, but unfortunately there is some problems with respect to the number of deadlocks. And we saw its instance, and we discovered that the reason it's because the decentralized approach actually accumulates delay, letting trains wait, but avoiding deadlock in that case. So we are fixing it. If we see on this other table, then you will get the time of win, draw, lose with respect to the accumulated delay. And as you may see from the first row, we are basically always winning or drawing with the decentralized and always winning with respect to the other 2. And this approach is actually, this result is actually replicated down below for the other tests, where there are where there are larger instances than the training set. So this was the first part. So we arrived at the station, and just take a deep breath because we have a few times, so we're just keeping to the next problem, which will be related to the train dispatching, but the approach will be a little bit different. So we are talking about the job shop scheduling problem, and this is a work with Marta Monaci from Sapienza University of Rome and Valerio Gasucci from Sapienza University of Rome and Optrail. So go back again, fresh start. The job shop scheduling problem. So similar to the other one, but here I wanted to show you the picture of the robots in a warehouse because I think they're nice looking. So there is basically a bunch of jobs and a set of machines doing some services. And for each job, you have a set of order tasks that each job has to perform on the machine. It's a really standard problem optimization, really maybe one of the oldest one, and it's been studied a lot. So we just thought, why don't we use these new techniques and see how it goes? Of course, the objective here to make it all simpler would be just to minimizing the max span. Some notation: J, the set of jobs; M, the set of machines; O, the set of tasks or operations; and I will just, yes, and we will identify with J, K, a task, so a couple J, job, and K, machine; PJ, is the processing time, so how much time do we need to do the task. TJK is when we start the operation JK, and CJK is the completion time. So it's basically the summation of starting time and processing time. We make a couple of assumptions, really common assumptions. The first one is no preemption, so operations cannot be interrupted, and no overlap. So each machine cannot process more than one job at the same time. As I said before, the objective is the minimization of the maximum of the main span, which is the maximum completion time for all the operations. Okay, so the first thing we have to do to use reinforcement learning into the job shop scheduling problem is actually to think to the job shop scheduling problem as a macro decision process. So first of all, what a macro decision process, MDP, is defined by these 4 elements. So the first one is, again, S, the set of states, A, the set of actions, R, the reward function, and P, the transition function. The data structure, as I said before, is a list of jobs, and each job is a list of tasks. So if you look at the picture, you will have that here, this is kind of the, here, this is kind of the normal state, where we, as you may see, the number of jobs may vary from instance to instance, and for each job, the number of iterations, the number of operations may vary from one job to the other. Okay, so after we observe the state, then we have to choose an action, and the action, as you may see in the next picture, it's basically all the operations that are available for each job to be processed. And our action will be just to choose one of them. So after we choose one of them, what happens is that the job length is here, last picture, the job length is actually reduced. So other than having different number of jobs for each instance and a different number of operations for each job in the same instance, the number of operations is changing from one state to the other. So this is a big challenge. Okay, this I already said my was. The reward here, since we are in reinforcement learning, we are maximizing, so we are taking the negative delay, and this negative delay, of course, since we are doing with we are dealing with the max span, will be this negative value if the completion time of the operation we are processing is exceeding the local maximum completion time reached so far, 0 otherwise. And with this property, at the end, we'll get that the summation of all the reward, the negative summation of all the reward will be actually the max span. We decided to use the Proximal policy optimization algorithm, which was first proposed in 2017 by Schulman et al. And we are using here a version of the algorithm that doesn't use clipping, but it's just an unconstrained optimization problem, because we found out that using directly the unconstrained version was leading to better results. So how does it work? Basically, we, instead of we are updating the actor by maximizing an approximation, a surrogate function. Sorry, and the surrogate function takes as input an approximation of the advantage using some sample efficiency minus a penalization term, and this penalization term is actually divergence, a callback-Lyberg divergence between the our policy and the previous policy in the iterations of the algorithm. Beta is updated using this rule. So basically looking at the diversion and to an hyperparameter delta. And this actually is made up to balance the trade-off between exploration and exploitation, which is quite crucial in this kind of stuff. And whether the critic update is quite simple and it's just done by mean square error. Okay, before we see the results, we just need to exploit the last problem. So the last problem is how we build up our agents. And our agents, as I said before, they need to be flexible. And they need to be flexible on several degrees of freedom, on several dimensions. So what we decided to use is actually two concatenated LSTMs in order to deduce the variability of the dimension of the input. So the first one will deal with a variable number of operations, and the second one will deal with a variable number of jobs. After that, for the actor, we use an action masking and a softmax function so that the output will be this one, which is kind of an approximation of a probability distribution for each action that can be taken. Whether for the critic, we will just use an encoder with a fully connected layer until going to a scalar. So it's basically the structure is basically this. So where we have first LSTM, second LSTM on one end, action masking on the other, an encoder. This is quite new. Okay, so let's see some experiments. I don't want to enter too many details. The basic thing is that we start here by doing the training, starting with instances from 8 jobs times 6 machines to 20 times 15. And we have 200 of them, and the processing times are drawn by a Gaussian distribution. And I want just to underline the fact that we use a standard computer to do this stuff. So we didn't use any weird massive server, just kind of our thing. Because we wanted to do that. It's not that yeah. So the training, let's see a couple of pictures to see if we are training something. So this is the value function. And we start from I and we go down. So yes, we're learning something in the value function. And here you may see the normalized reward. So for each group of instances. So basically, we are going to fix ourselves to a certain strategy, a certain policy.
Sorry,
okay.
you have a couple of minutes. Okay.
Yeah, I have a couple of minutes. Perfect. So what this is it's perfect. I'll show you just a couple of slides. These are the tests we've done. So if you remember, they were really small instances. Now we go from 30, 25, to 50, 45, which are instances way much larger than the one we train on. And we use also a couple of distribution for the processing times. The first one is still Gaussian, whether the second is Poisson. In order to, we thought that the Poisson would have helped Cplex, our competitor, but it didn't. So we made a couple of analysis, one on the computational time and one on the objective value. So I will not show you the tables because I don't have time, but they're nice looking. I will show you the performance profile. So if you don't know performance profile, basically the higher curve wins. So we are the higher curves here. We are winning on the computational time, so we are reaching better solution faster. But of course, this is a heuristic, so we're not going to the optimal thing. but the nicest thing, in my opinion, it's actually the objective. The objective. So given the same amount of time, the bound that we are able to find, and it's actually way much better with respect to the simplex in this case. So 2 minutes, I thought I covered it. So thank you everybody for listening, and these are some of the references that I've used. Thank you.
Okay, thank you, Giorgio, very much for your presentation. Now it's time to the audience. If they want to ask something, you can type your question on the chat or raise your hand, and I give you permission to unmute yourself and put your camera on if you want. Pose your questions.
Can I ask first? I have actually one question to Antonio. So I think it's maybe usual question. Can you extend your methods for other norms, not only Euclidean one, but I don't know, L1 or L infinity, in order to cluster?
Yes, it is something we try to do, but the problem is that we cannot easily derive an SDP relaxation for a generic norm.
Oh, so you need this matrix form in order to be able to make this transformation. Okay, thank you. And also just about must link and cannot link constraints. Am I right that it's information from outside, you give it to your model and you can...
Yes. In our case, in this case, must link and cannot link constraints are derived from branching decisions. So whenever we have to divide our problem into two sub-problems, we add a must link constraint on the sub-problem on the left of our tree, and on the right must link constraints. So in this case, this is not a true background knowledge. It is extracted from the branch and bound search.
But for example, if you have this knowledge from outside, can you add it somehow to your model?
Yes, this is what we did recently. We extended our algorithm to deal with the semi-supervised case with the must link and cannot link constraints from the beginning. Yes.
Perfect. Thank you very much. Thank you.
Thank you, Sinia, for your question. Are there any other questions from the audience? Okay, so
I want to say to Giorgio that it was an excellent presentation, but I'm not an expert in reinforcement learning, so it is why it's maybe difficult to completely understand what is going on in your model. But it was really interesting, and the applications are amazing.
Thank you.
Yeah. So I don't know if there are no questions. Yeah, we can call this seminar, but of course you can write your questions to our speakers directly on their emails if you need something, and the video of this talk will be available on YouTube, so we can repeatedly constantly learn something new from this seminar. Yeah. Usually I watch some seminars several times, so if I need some information. Yeah.
Okay, so thank you to the speakers and to the audience for coming every week. And just recalling you that next week there is a talk from Coralia Curtis, and you all are invited. This is the last of this second session. So see you.
See you.
Thank you.
Thank you.
Bye bye.
Bye bye.